First of all, thanks for the invitation to this webinar. This is an interesting exercise. I've had great interest in laser spectroscopy for a number of years now in my former position where we've used it for research. And now since I've moved to the IAEA a couple of years ago, I'm even more involved in this. And the reason is that the agency is particularly interested in laser absorption spectroscopy for water isotopes, because that's part of our mandate, is to encourage nuclear technologies in isotope hydrology. And certainly lasers have been playing an important and increasing role in our outreach efforts to promote nuclear techniques in hydrology. Now, part of that is that I've been involved in training exercises for the last couple of years with member states and new trainees coming to the agency for training purposes. That's opened my eyes a little bit to issues beyond the research side of it. And so that's what I'd like to cover in the next half an hour or so. I'll cover some of the basic essentials, again, mostly speaking to newcomers to the technology, covering some core ground there, but just for the rest of us who are interested in R&D, I'll show some interesting data as well. Okay, now let's just take a global Google Earth view of water isotope performance, and this is what I'm showing in this slide here. On the is the WICO, the International Intercomparison for Water Isotopes that the agency ran a couple of years ago. And the panels on the left, on the top two, show you the results for lasers results, and the bottom shows you the results for isotope mass spectrometer results. And again, no distinction is made over brand or the types of peripherals used here. But you can quickly see on the left side there that the results agree pretty well. Now, this is pure water that was sent out. Another interesting thing is that about half of the labs that participated in the last international test, of the 169, were laser laboratories now versus 0% in the 2007 test. So this also attests to the rapid adoption of lasers in both new and in current laboratories. And I rather suspect a good proportion of the increase is in new laboratories. Now, you can see from the table down below there and from the graphical figure on the left is that there really was not much of a significant isotopic performance difference, either for deuterium or O18, based on either technology for pure water. But when we dug a little bit deeper, we found that the primary cause of poor performance, or outliers, seemed to revolve around the handling of standards and calibration, which incidentally affected both technologies equally. And so this is where I'm going to start, is with at ground level, because this is one of the major problems, and this is one of the recurring questions I get at the training courses, is how do we get started? You've purchased your instrument, you want to get started, and the first thing you're going to face is how are you going to get good results, and for that you need laboratory standards. The other fact is that the lasers consume a lot of lab standard water. Lots of auto runs, long auto runs, little vials you need to fill up. And so there's a more pressing issue with how you come up with laboratory standards and maintain them over time and maintain the isotopic fidelity so that you get the best possible results. And as I mentioned, this is a particular issue for new laser labs that have staff that may have little experience, that don't realize evaporation is a problem, and those sorts of things. Another issue that I run into on a recurring basis is new laboratories in particular, where they are trying to get an appropriate standard delta range and a control standard, and in their particular location, there happens not to be a wide range available. And so getting and obtaining standards is a problem as well. And then finally, of course, maintaining accurate performance in QAQC over the long term is of critical importance as well. Now, for this crowd, probably most people know the calibration scale, of course, is the VSMO SLAP scale for O18 and deuterium, as shown on the top here. And VSMO, VSMO2, and SLAP 2 are the primary standards that are used for O18 analysis and calibration of waters. And of course, they're only available to you on a limited basis in a small amount every 3 years or so. Now, practically speaking, most natural water samples, fresh waters, for example, lie somewhere between SMO and GISP, as shown by the arrows there. So what we really, as a user, are looking for is a set of two laboratory standards that more or less encompass the user range that you will encounter in your samples. So what you're looking for is a low, perhaps somewhere around GISP, and a high around 0 or even slightly higher. And of course, you want to have an independent control that's located somewhere in the middle. Now, where can you get laboratory standards? For your laser, you'll require at least 3 reliable lab standards for your daily use, and particularly so when using LIMS for lasers, which I'll touch on a little bit later. The 2 daily use calibration standards are a high and a low delta value standard, and these, of course, must fully bracket the range, the isotopic range of the samples that you'd be measuring routinely in your laboratory. And secondly, or thirdly, you need a control standard, which, again, as I mentioned, should fall somewhere in between. Now, lots of laboratories, of course, like to have more than just 3, and so a library of 3 or 4 or 5, 6 or more, that's fine, but it's not essential. But you have to remember that, you know, a linear regression of multiple standards doesn't follow either the IEA or Reston recommended 2-point normalization procedure for delta scale expansion compression, as it also works in LIMS for lasers. Where can you get laboratory standards? The primary standards, of course, VSMO, SLAP2, GISP, and so on. Well, GISP is not one of the calibration standards, but these are available from the IEA for purchase. If you are from a developing country, you can probably get it for free if you make the request. And of course, the USGS maintains an excellent stock of well-calibrated laboratory standards, and also has I believe they have VSMO still, original VSMO as well. For daily use, there are in fact few, let's call it authoritative suppliers, generally sold in small quantities and can be rather costly. The USGS in Reston, Ties Laboratory, has an excellent offering. They sell cases of 144 glass-sealed ampules, which roughly translates to about a 1 or 2 year supply for the typical user. And the link is given there. The IEA, we can provide some cost-free starter kits of standards, and this is primarily aimed at new laboratories and developing laboratories around the world. I'm also aware that the laser companies themselves provide starter kits of laboratory standards. Don't discount your colleagues or other laboratories. Many laboratories are more than happy to share a little bit, usually not a large amount to supply you for a long term. And finally, probably the most cost-effective way is to produce your own laboratory standards. And that's probably the most inexpensive route. So how do you make your own laboratory standard? Well, it's actually quite simple. You just need to have a wide, sufficient delta range, but collect the clean water for your laboratory standards. And at this stage, the collection stage, you can just use an inexpensive plastic jug. We recommend that you collect at least 10 to 25 liters for each of the standards, if possible. And as I mentioned previously, this could last you for a decade, if not more. It's probably best to deionize or distill the water to guarantee that there's no contamination from organics. Now, that may or may not be an easy thing to do for some laboratories. For your high delta standard, if you're in a particular location, you may consider groundwatering at the coast or low latitude, or do your own distillation or evaporation to get a high delta value. For a low standard, you could either, if it's available, you could melt snow or obtain ice from a high altitude or a cold climate. And for a control, you want to use something in between. So that's something that you typically would be measuring that's similar to your samples. One possible tip, it seems to be quite a challenge to get a low delta value standard. And one tip is to get imported bottled water. And I've just included a figure that I found on the web that they are selling Alaska glacier melt water as drinking water. You could buy perhaps a case of these to obtain a low standard. One of the critical things about laboratory standards that is often overlooked is proper storage. You need to store these laboratory standards in either sealed metal or glass containers. You want to avoid heat, sunlight, or any conditions that would promote evaporation or leakage or biological activity. You can use small bottles for your bench top to minimize opening and closing the main storage containers. And as shown in the photo here, bottom left, these are simply commercial, inexpensive beer kegs where we've added a fitting at the top. It's basically made of standard swage lock parts, where we have a siphon going down to the bottom, and we can overpressure the keg to a couple of bars pressure, or using argon or nitrogen gas. That allows you to monitor the pressure, so you know there's no leakage. And secondly, it's an easy way to dispense the laboratory standard into your daily or weekly use vessel. That's shown on the bottom right there. This is how we do it in the agency laboratory here. We use ground glass stoppered bottles, and you can see the various sizes there that are available. And generally, the one on the far right, or the middle one, somewhere between 50 and 200 milliliters, we fill those ground glass stoppers, and we use those. Importantly, is you don't want to let the volume drop below, and this is simply a rule of thumb, it's not proven, below about 50%. During training, I've noticed, and visiting laboratories, I've seen some laboratories where their laboratory standard was just a small layer of water on the bottom of a large canister. This is obviously not what you want to happen. You don't want the laboratory standard to evaporate within the container that you're trying to keep it sealed in. Calibration, you can either send it out to reputable laboratories, or you can try it yourself. And again, if you are a new laser laboratory, you should probably get your hands on VSMO2 and SLAP2. You'll only be able to do that every 3 years. What I have seen done in a couple of cases is people get a laser, they get SMO and SLAP, and they start using that routinely and use it up very quickly, and then are at a loss what to do next. So the first order of business, if you do have the primary reference materials, you don't want to waste these valuable materials, is to produce or to calibrate your own laboratory standards. You need to perform enough measurements, I would say again, at least 10 times for each of the standard to get statistically defensible results. You probably want to repeat this calibration over a few days just to enlarge the data pool for evaluation. And, of course, many laboratories are more than happy to assist. So if you've prepared a laboratory standard, you're not sure if you're getting good results, you can send it to the agency. I'm sure there's other laboratories that would be more than happy to run it as an independent check. At this point, you should have some confidence in the results of what your daily use calibration standards delta values would be to use. So once you've got acceptably precise isotope values for your internal laboratory standards on the VSMO SLAP scale, you would then use those values and those daily use laboratory standards for your unknown samples. You can add these values into LIMS for lasers, the reference table for automatic calibration or normalization. And as I mentioned, you need to carefully protect your laboratory standards to prevent any kind of evaporation or leakage. Plastic bottles, not a good idea, particularly if they're not high-density polyethylene. Again, if you can go with metal or glass, there are some low-cost ways that you can do that to ensure that your laboratory standards don't evaporate over time. Finally, you want to track your control standard. You will monitor this both on a daily basis and a weekly basis, and you'll be looking for trends over the long term. And that can be done within LIMS for lasers using the Track My Lab QAQC feature. So just to reiterate here, and maybe this is some old news for many of you, but again, it's one of the things that we come across repeatedly, is that storage and improper use of lab standards appears to be one of the weakest links in the chain for top performance. And it really comes back down to garbage in, garbage out. If you don't have good laboratory standards, of course, you'll produce terrible results. Okay, part 2 here, I'll briefly touch on this. We've introduced LIMS for lasers. This was a co-effort between the USGS and the IAEA in 2012. Its primary rationale was, again, to address the rapidly expanding numbers of laboratories that are using lasers for their liquid waters. And we found that we're having great difficulties processing data. So the instrumentation is, in fact, relatively easy to install and operate. You can do it in a day or a few hours or so. But the routine laboratory operation is made more difficult because these machines produce a lot of data that you need to manipulate offline in Excel to obtain final results. And I'm glad to see some progress here, but the fact remains that the manufacturer's software currently puts out CSV files still, and that's not suitable for sample and data management over the longer term. Just a couple of examples here. This is the type of output files that you get from both suppliers. You get a huge CSV file. If you've got large numbers of samples, this is immediately the file that you're faced with trying to process. And what are those processes that you need to conduct? These are, I would say, 6 or 7 required data corrections and checks that you need to apply to that CSV file. The first order of business, if the laser software hasn't already flagged it, and as I mentioned, it looks like there's some improvements coming there, is you need to find those bad samples that are based on H2O concentration. This could be due to a faulty syringe, for example. You may need to ignore the first 2 to 4 injections to reduce the between sample memory, as Kate was alluding to earlier. Then you need to determine and apply this between sample memory correction to correct the remaining data. You may need to check and adjust for instrumental drift. Now this can be either linear or nonlinear. Finally, you need to normalize the results to the Wiesmo and SLAP scales. And importantly, you want to keep track of your control standard and over time using to monitor your QAQC. And of course, importantly for many laboratories producing lots of data, you want to be able to keep a track of your clients and projects and samples, and this is very difficult to do in Excel. We've tried it with spreadsheets. The IEA has produced a very complicated spreadsheet which we published a number of years ago and which has been sent out, but very quickly it's a frustrating exercise, particularly for new users, with reams of columns and cut and paste and graphs and so on. And so this was the primary motivation for LIMS for lasers, just try to make it easy for people to process their laser data. This is just an example of the interface. Basically, the software flow is a workflow. We start with our projects on the left. We create sample lists. We analyze the results to the far column on the right, down, and evaluate our results. And finally, when they're acceptable, we store them, and we can access them again from the first column, which is the projects menu. I might add, this software is based on LIMS for stable isotopes, which I believe I saw the first version of that in the early 1990s. So it's a mature product. The code underneath that is sound, and it's been available since 2002 in a streamlined version for lasers. It works with all lasers from all manufacturers, and it's free. The software is available from the links given on the screen there. I mentioned some of this already. Again, fairly easy to use, and more importantly, in the blue, it automates all of those required checks and corrections that I alluded to before with just a few mouse clicks, so no more spreadsheet nightmares. The use of LIMS for lasers also encourages the IT, or identical treatment approach, to the use of systematic analysis templates, which has long been proven to give the best results. It's very easy to manage multiple laser instruments. You can have 2, 3, 4, as many as you want, all functioning under the same piece of evaluation software of LIMS for lasers. And again, as I mentioned, it's a complete project sample management package that's suitable for the long term. Here's just a couple of screenshots. This shows you a QAQC evaluation button for monitoring your control standard over time for either one or all of your instruments. It displays outliers, weekly and long-term trends, and more importantly, using a control gives realistic performance statistics. The figure that you see here is for our IAEA control standard that we've used, and this shows results for all of the lasers that we've used over the last 2 years. And you can see on the bottom, and really translates to about 850 analyses. And you can see that the mean delta here has precision on the order of 1 per mil for deuterium, which is actually spectacular. And for 018, the story is not quite as good as it is for the dual inlet mass spectrometers, which are about a factor of, I think here we're about 0.05 or so. So you can see that it's still quite good, but the 018 is not quite as good as IRMS. As Ty alluded to in the previous talk, we're going to be releasing an update and are working with the manufacturers to keep up with their latest technologies. And for that, we're adding the 017 capability as shown in this particular plot here, or this graphical screenshot here. Again, 017 import, and also we're retaining the same data processing features that we had with both deuterium and 018. meaning that you can correct for intersample memory and so on, and linearity and drift and so on. So those are all retained and will be made available in the near future. Another feature that was came up out of the training courses was the earlier version of LIMS for lasers would simply import the data, and it wasn't until steps later that you realized you might have had a problem with your syringe. Now, upon first import, and this looks a lot like what Elena was showing with the new LGR software, is that it gives you an immediate graphical display of the water amount in your cavity before you import the data. So at a glance, you can tell whether or not your syringe has had problems or that you've had some sort of other issue in the laboratory that has caused the water concentrations to vary unacceptably. Okay, so that's LIMS for lasers in a nutshell. The third thing that I quickly ran into when dealing with lots of people here is many questions about how do I know how well my instrument performs. And it led us to think about ways that we could test instruments and come up with some kind of a universal approach, let's say, where we could look at instrument performance and accuracy using some well-established techniques. This was published in the reference given below this month, actually. And it's basically a systematic test to help laboratories see how well their laser instruments are performing. To do that, we need to have some reference and test waters of well-known isotopic composition. And the table 1 there shows you the references that are available. In fact, they include SLAP2 and VSMO2. But again, as I mentioned, since those are only available to you every 3 years or so, you can also substitute those for the USGS-46 and 48. The delta values are given there on the right. These were exceptionally well calibrated at the USGS laboratory in Reston. So you could consider those your primary samples. The second thing you'll need is samples, which are denoted as A, B, C, and D here, where you also know the isotopic composition very well. And there's some suggestions given here. For example, JISP or USGS-47 or 45, which lie in between SMO and SLAP. We left a couple of blank spaces there called lab standard high and low. These would be possibly your own laboratory standards, where you've already got some numbers or you've had numbers provided to you where you can see how well you can meet the accuracy and precision criteria. We also use LIMS for lasers for doing this performance evaluation, and this shows a systematic performance template consisting of 8 injections, ignoring the first 4. And you can see the second column there is simply the run order. So we start off on the left column with a couple of deionized water injections just to prime condition the instrument. And then we start with this sequence, which has a number of functions. So we start with a low standard, and then 2 high standards, and then triplets of our samples, and then repeat the sequence but reverse, so high, low, 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 high, high, and so on. What that does is it shows the function of each of those are shown in the 3rd, 4th, and 5th columns of what those things actually do. So the high and low standards are obviously used for data normalization. But the fact that we have, say, a high and 2 lows or a low and 2 highs also allows us to quantify very well the between sample memory, which is then a correction that's applied to all the data. And lastly, we can use the same standards to check for instrumental drift over the course of the auto run. We came up with a proposed, and this is proposed, I mean there's many ways to do this, a proposed weighted scoring evaluation system based for performance for both isotopes. The principle here is that the more accurate you are, in other words, the more closer you are to the correct value, you get a higher score, where accuracy results either in a slight reduction in score, where it may still be acceptable, and you can see the criteria in the 3rd column there. Just as an example, for 018, we're saying its excellent performance would be less than a 0.08 per mil difference from the known value. Acceptable still, given that we know the laser's 018 performance is perhaps not as good as IRMS, is somewhere between 0.15 and 0.08 difference from the known value. But we draw the line at 0.15 per mil. If you can't be within 0.15 per mil of the known value, then that we would consider unacceptable performance. And ditto for deuterium, a similar kind of scenario. Down near the bottom, it's not highlighted very well, but we do build in precision as well as being either unacceptable or acceptable. And again, the criteria are given for there, and that's simply a score reduction. So we tested this a bunch of times, and it seemed to work quite well. And I think I think Elena showed this top one here. This is just examples from both later model Picaro and LGR instruments. And I know it's a messy table here, other than to show the fact that both of these instruments passed. And you can see the supplier name, the model used, how we measured the isotopes on these, the sample rate, the carrier gas used, the year built. And again, what's of primary interest is the third and fourth columns for both. Is you can see the measured value, and that, of course, by measured here, I mean the value that has been obtained using the instrument, your calibration standards from the first table that I showed you, and the normalized results relative to VSMO SLAP, and then compare that to the known value, and then looking at the differences. So this seems to be quite a robust way to evaluate our laser instruments, and it probably would apply equally well to RMS. Now, beyond that, this is something you may want to do a couple of times a year just to double check, make sure your instrument is working fine. But on the day-to-day basis, you certainly don't need to go to that extreme. If your instrument's running well and you've done this test, you can go ahead and proceed with day-to-day runs. And this is just a simple example of a 20-sample template, but we use the same principles here. We use couplets of high and low standards, bracketed normalization, drift correction, intersample memory, and it's just showing you here how a sequence could possibly look. In general, we recommend 8 injections, ignore the first 4. Now, that may change, of course, as instruments improve. It may be slightly reduced, but certainly this would be a good conservative place to start. As I mentioned, the placement and the arrangement here allows for automated drift and memory correction in LIMS for lasers, and the control must be appropriately placed. Now, what I mean by appropriately placed is you'll see midway down the left column there, the control follows samples. Now, I have seen laboratories where the control is always placed after standards, the same standard, which really does not form a randomized or a well-placed control. It really should be mixed in either randomly with the samples or following samples and not have placement bias. Okay, so that more or less covers some possibilities that we can use and that you can use for your laser laboratory to evaluate how well the machine's performing, and some suggestions to get good results. And we've had good luck with that. Now, I just want to talk a little bit more about day-to-day issues, sample handling, and daily operations. As Ty alluded to, water samples should be fit for purpose. That means oily waters are probably out. Generally, clean natural waters pose no problems for lasers. We rarely encounter problems with rain or ground or river water. Sample collection is also of critical importance. You collect and filter and store your waters. Your samples should be collected in high-density polyethylene or glass bottles with tight caps to avoid leakage. You probably want to dispense your unknown samples into the 2 milliliter vials just prior to analysis. We have run tests to show that unpunctured vials will last at least a month, but it's probably good practice just to dispense just before. If you've run a set of samples and discovered you needed to repeat it, the punctured vials, you can reuse them again, but we strongly recommend that you discard those after 2 to 3 days. The septum has been compromised, and there is potential for some barometric pumping and evaporation out of the vial. So that's one thing you may want to consider. If you have to repeat, probably best to put new caps on it and set it aside for a repeat. There are problematic samples. This has been alluded to or already discussed in the previous talks. Salty waters, why are they a problem? Well, from our experience, they usually result in your syringe jamming up pretty quickly as salt may precipitate or get stuck into the injector, into the needle barrel. And as well as was mentioned, that you would actually get salt buildup in the injector. And these salts, of course, will impact memory and variable results, particularly for 18. And as already mentioned before, waters containing VOCs, volatile organic compounds that interfere with the water isotopes, they can lead to highly erroneous results. And these would be things like organic leachates or plant extracts, oily water gases, landfills, and so on. So caution is involved with those, is required for those type of samples. On the day-to-day, let's just talk for a minute about syringes. This is your most expensive consumable. These syringes cost about $100 US each. And it's a real bummer when they break after about 10 injections. And that, there's various reasons for that. You might have not set the instrument up properly, or you just have a nasty sample. Again, syringes are easily destroyed, but with proper care, probably can last for 1,000 to 2,000, 3,000, 4,000 injections. I've gotten that lucky. But it's a good idea to keep 4 or 5 in stock. There's nothing worse than having a syringe break only to discover you don't have any more and have to order it and wait 2 or 3 weeks to get syringes in. So my recommendation is keep 4 or 5 in stock. Now, that's a bit of a pricey purchase, but it's part of the cost of doing this business. As syringes go bad, the plunger often becomes sticky and will underperform. And by underperforming, what I mean is you may not get the proper or full injection. And you may see variable results in water yield. And as Ty showed, if the water injection isn't reliable and consistent, you can get very highly variable results. That has improved with the newer instruments, but that effect still exists. And again, as I mentioned, salty samples. And I would set the bar a bit lower, possibly around 20,000 milligrams per liter as total dissolved solids. Those types of samples can also quickly seize syringes if you're not doing some preventative care. Now, by preventative care, there's a couple of things you can do here. First of all, you can start your run with deionized water as a dummy. Also, end your auto run of more saline samples with a couple of vials of deionized water. That will hopefully wash some of the salt out of the needle and not have it seized solid the next morning when you come in. It also helps to precondition the instrument if you wash your syringe of solutes. I strongly recommend priming the syringes in deionized water offline, not on the autosampler, before you stick it into the autosampler, just to ensure that the barrel has smooth action. You'll often find they're a bit sticky after a day of running, and it's sat overnight drying out. So that helps a lot to keep your syringe life long. Some have proposed solvent cleaning between runs. I personally haven't done that. Others have suggested storing syringes in deionized water. That's what we do here. We just have a little vial with deionized water and let the syringe be filled with deionized water and store it that way. The bottom line is bad syringes or underperforming syringes will yield bad results because all instruments are somewhat sensitive to water amounts and highly sensitive in some cases, as we've seen, and you need these accurate and reproducible injections. Some people go to great lengths to try to repair the syringes. It's not a job I'm particularly fond of, and again, my recommendation is just build this into the cost of doing business. You can spend hours tinkering with a syringe trying to fix it. It will probably lead to more frustration than anything. Just on the operational side, as I mentioned, my experience with trainees coming here and with laboratories that I've visited on behalf of the agency is that data management is one of the hardest parts for most people. So you can automate it to a large degree using the free LIMS for Laser software. There are what we call bad days when whole auto runs go bad for a variety of reasons. It could be the syringe underperformed, and this usually happens at 6 p.m. after you've left the laboratory. It's better to redo the run over trying to fix bad data. I mentioned this before, repeats. If you have to repeat, make sure punctured vials aren't used for more than a couple of days, or recap with new unpunctured caps for repeats. And importantly, use fresh measurement standards and control standards for your daily auto runs. Don't let those sit around getting stale. And again, as I mentioned before, you want to protect those as much as you can. Just a note about repair and service. I've had experience with the early generations of instruments, and they're surprisingly robust. My suggestion would be to budget approximately $1,000 a year for hardware problems. Now, you may get away with 2 or 3 years without any problems, but then have a $3,000 or $4,000 bill, depending on what can go wrong. Now, what can go wrong? Often it's valves internal in the instrument, or electrical components, hard drive failures, these sorts of things. I've seen pretty much all of those. The other thing is that DIY, do-it-yourself internal repairs really require some sound engineering and electrical support staff. It's not something, they are kind of black boxes for a reason. If you open it up, you may be baffled by what you see. I would suggest that they're not easily serviced by inexperienced users. Which leads me to one of my pet peeves is the laser service model that we are stuck with today. Generally, when you run into serious problems, the response from both companies is send the whole unit back to California. Now, this is costly and really inconvenient for many international users and results in long downtimes. So again, I would encourage the companies to try to, I know it's not possible to do it in many cases, but to try to make user serviceability something that can be looked at into the future. And I think it was Elena alluded to that about the cleaning. All right, trouble. Let's talk about trouble. Bad spectra and water yield. In my experience, when something goes wrong, I get calls, emails from people that we've supported. I would say 95% of the time it's the syringe, and people will say, I've changed it, and I say, check it again or try a different one, and often it's the syringe. Microliter syringes are actually sophisticated little devices, and when they go wrong, they go wrong. So again, as I mentioned, keep a stock of new syringes in hand. You could possibly have a septa leak due to how you've installed it. It might have twisted as you've put it in, or there could have been a leak developed in the transfer line, or when you've assembled it, you haven't got a connection quite tight. Inlet tubing leaks are a good place to look for these sorts of things. These can result in sloping baselines, erratic yields, and so on. And dirty mirrors, people tend to look for the worst possible thing, or disease, if you want to call it that. Dirty mirrors, I would say only after a lot of abuse. And then just a couple of screenshots here, just showing on the bottom left, that would be a jammed syringe on LGR. It's basically no water getting into the cavity. And on the right, we have a leak between the vaporizer and the analyzer on a Picaro instrument. And again, that's simply from their website. So there's lots of troubleshooting techniques and advice you can get from the websites of both companies. Spectral contamination, I don't want to beat this to death, but it is a bit of an elephant in the room. Again, as mentioned, alcohols, methanes, ethanes, VOCs can cause spectral interference and bad results. So great caution is advised if you're looking at water samples from landfills or sewage samples or contaminated sites or petroleum or gassy sites. I'd suggest that it would be best, if there are questionable samples, that you check every auto run with the offline evaluation software. And more importantly, when data are flagged as compromised, don't accept the results. You need to reject those. Now, you may not be in a good position to reanalyze samples by RMS. So this is a bit of it's easy to say when you have both, but if you only have a laser lab, you have no way of knowing sometimes whether the results are good or bad. So this is a bit of an issue that could be discussed. Some corrections may be possible using supplier software, and I'm very pleased to see this developing quite nicely in both cases using either the SCI or ChemCorrect. Again, these, I think, if I'm understanding correctly, these require some kind of training for known contaminants. So as was mentioned also, we don't know often what's in the waters and if they're causing contamination. So if it's not in the library, you cannot correct for it. Okay, saline samples. You can certainly load them up and have your machine have a go at it. You'll just find that your syringe will probably fail more frequently or fairly quickly due to salt buildup in the syringe barrel. Again, buildup in the injector, memory and clogging. And so, again, as illustrated in these photos here, you need to clean your vaporizer or transfer lines after running these salty samples. And again, I mentioned previously the priming or the washing of syringes following salty samples. Nobody really talked about tracers. This has been a bit of interest here because we have a tritium enrichment lab where we're wanting to use deuterium for doing the enrichment calculations. And we've quite nicely measured deuterium values up to 20,000 per mil with an error of plus or minus 60. This just shows some other enriched samples that were run for both O18 and deuterium in the laboratory here, well outside the range of natural waters. But again, comparing the laser and the RMS results, and we see remarkably good agreement on clean waters. Of course, if you go the tracer route, you really have to watch out for between sample memory effect, because if you have a change of 1,400 per mil between a spike and a natural water sample, even 1% carryover or 0.5% carryover is going to have a huge effect. Okay, I promised you to show a few newer applications. And for me, one of the most interesting things about lasers was the ability to measure water as water, which is something you can't do in IRMS. And to me, that opens up numerous avenues for hydrologic and environmental research that you just couldn't do previously. I'm just going to show you an example of work we did back in my former institute, looking at, well, actually all of these are from the former institute, looking at brines and cores. Now we mentioned you can use your laser, but note you may be able to use the same instrument in both liquid and vapor mode. For example, if you have a Picaro liquid water analyzer, all you need to do is pop off the vaporizer at the back and you have a vapor machine. So I'm just going to talk in a moment about saline brines as well as cores. There's some other applications regarding real-time isotope data. I think it was alluded to in the previous talk, both for flowing water through either the use of what was described earlier, or membrane contactors, or ice core melters for looking at ice cores. I'm not going to talk about those just for lack of time. But the really neat thing about this is that we can exploit new levels of isotopic detail to help us look at dynamics of water movement. And that could be in the subsurface or in paleohydrology. So the question I had quite early on with the vapor units was, can we get the isotopic composition of pore water or a brine or from a core just by measuring the vapor that's an isothermal equilibrium with the sample itself, whether it's a liquid or a solid? We came up with a list of advantages. We don't need a mass spec. We can do it on nasty waters, brine or cores. We don't need to extract or distill the water sample. We don't need to convert the water sample to hydrogen or CO or anything like that for IRMS. And, of course, we get both isotopes in the same sample. So what would be the disadvantages? Well, we couldn't think of any. Now here's kind of how this works. So I'll just kind of walk you through this. The principle here is that in a closed system, pore water will quickly diffuse as vapor into the headspace around it and attain 100% relative humidity. So the principle here is, rather than trying to get the water out of the core or getting the salt out of the water, let the water come to you in vapor phase. It's nice and clean. Under isothermal steady-state conditions, this equilibrium isotopic fractionation factor has been known for decades, the fractionation between liquid and water. And then you simply measure the headspace vapor using your laser to measure the O18 values. And then to backcast back to the liquid water, use a temperature-dependent equilibrium fractionation factor to back-calculate what the liquid of the pore water or the salt solution was. This is kind of illustrated on the left here in schematic and in real form. We simply use low-cost double Ziploc bags with double seals, and this shows here an example where we have a core material or we have liquid brine in the bag. We simply inflate it with dry air to about 1 liter, let it equilibrate, and then simply puncture a little hole and suck the headspace into the laser spectrograph. And the middle picture there shows a Ziploc bag with some core material that's been inflated and equilibrated. I'll just talk a little bit about saline waters and brines. Brines are particularly nasty because they often, particularly highly briny samples, will wreck your syringes, often after as few as a dozen injections or so. And of course, the more annoying problem of salt buildup in the injector and having to clean all that out. So we used, this is an example where we used the principle of liquid vapor equilibration here. This is for deuterium. What we simply did was we constructed, and each of the 4 panels here are different salt solutions going from 0 to 5 to 6 molal concentration, so hundreds of thousands of grams per liter. And rather than injecting these waters, we simply poured these waters into this bag with inflated with dry air, let it equilibrate, and then simply measured the headspace and looked at the again, the water we used was of known isotopic composition where we dissolved the salts in. And what you see here for deuterium is all of the published literature on equilibration with brines. And you can see there's some substantive isotope effects depending on the type of salt, whether it's calcium chloride or sodium chloride or magnesium chloride or potassium chloride. You can see there's a large effect. They say for sodium chloride, for example, on the bottom left, the isotope effect is on the order of +3 per mil per mole of sodium chloride. Again, in all cases, highly linear, which basically allows us to construct a correction algorithm to back calculate based what the liquid water actually is, in spite of the salt effect. This is for deuterium. You do exactly the same thing for O18, and you get these types of patterns. Now, there's more data in the literature on O18 because these were done by equilibration with CO2. But again, a simple correction algorithm can be produced. The black dots, I forgot to mention this in the previous, are done with lasers. The open symbols are from the published literature, as noted at the bottom of the figure there. For O18, for sodium chloride, bottom left panel, again, this effect is quite small. It's about 0.3 per mil per mole of sodium chloride. Now, what we have not done is looked at mixed salt solutions. That would be the next logical step to do to see how well that would apply to real-world conditions. But the bottom line here is not a speck of salt entered our laser. We were able to go up to 5 mol with many of these salts, and all the laser ever saw was pure water vapor. So this is kind of a neat technique that could somehow be automated.
Hey, Len, we've lost your voice.
He sent a text about it. He knows that he cut out.
Okay. Thanks.
Sorry about that. I was cut off. Is everything okay? Can somebody let me know?
We can hear you now.
Okay, all right. Sorry about that. I don't know what happened there. Okay. Last application I want to talk to is about pore water, soil water isotopes. How we can do these with lasers nowadays. And just a bit of a review. If we're looking at pore water, and this would be groundwater would be included into this as well. I'm just throwing that in there. There's a couple of ways you can do it. One would be what we call in situ methods. This is where you would install wells or monitoring wells or piezometers. And these are used typically for the long term. You sample water repeatedly by bailing it or just sucking it out with a pump, and you take that water back to the laboratory and measure it. This is great for long-term temporal trends in monitoring. A second method is what I'd call the one-time snapshot. These are extrinsic methods where we take a core, as shown in the bottom picture, a geologic core, and you basically would extract the water from that and measure it for the stable water isotopes. Now, this is the classic toolbox for getting pore water from soil or unsaturated soils, low permeability, geologic formations. And there's about 4 or 5 methods listed here that have been used over the past decades. One would be for unsaturated for unsaturated sampling by suction using lysimeters or absorbing wicks. High pressure squeezing of the core would be another way to try to squeeze water from a core. Cooking is another one I call it, basically vacuum heating and cryogenic distillation, again using core material. The use of chemistry, the so-called azeotropic or toluene distillations to separate water from the core and to isolate it. Another technique is by mixing, essentially using a radial or double reservoir diffusion cell. And finally, high-speed centrifugation, where you basically spin the water out of the core. Now, in all of these cases, you end up with some water that you need to measure using either a laser or an IRMS. All of these above methods suffer from cost, time, complexity, issues of fractionation and so on, and contamination from drilling muds and poor precisions in general. Now, what I mentioned earlier, and this is basically how we are doing this now, is we simply use this idea that we can get the water to come to us by using core in a closed system filled with dry air. We simply take core material, put it in a double sealed Ziploc bag, inflate it with dry air, and simply allow the headspace to come into equilibrium, which happens fairly quickly. Isothermal conditions are ensured to ensure that we know the isotope fractionation factor between the liquid phase and the vapor. And again, we end up with 100% relative humidity in the headspace, which you then can use on your laser. The only trick is that you need to allow enough volume to be able to have about 300 or 400 seconds of headspace sampling at various flow rates ranging between 30 to 200 mils per minute, depending on the instrument that you're using. And of course, you have to empirically determine the equilibration times for low and high permeability cores and soil samples. Here's just an example for sand and clay. Just looking at the graphs on the bottom there, let's just look at the one on the bottom left for deuterium. This is where at T0 is where we've stuck the needle from the laser into the bag, and we started sampling the headspace of the soil that's in equilibrium with the vapor in the headspace. And you can see that at about 300 seconds, we've more or less reached a plateau. And we basically averaged those results using 10-second averaging for 100 seconds to get the final raw results there, which then we need to convert back to liquid values. For sand and soil, the equilibration time often is less than 30 minutes. If you're dealing with low permeability materials like clay, we find that the equilibration can take up to 3 or 4 days. And if you wait too long, by a week or two, you start to see signs of evaporative loss. Here's another fascinating part of it, is that we can go to extremely low moisture contents. Now, this has been updated since this was published. This is from 2008, and we're showing that you can see as the moisture content, this is the bottom axis for both O18 and deuterium. This shows as we're below about 5%, the results start to strongly deviate from the known value. We've since improved this and can get good results to as low as 0.5% moisture content. So this means literally dry sandy materials, dry soils. And so this method can also be used on unsaturated geologic cores with great success. Now I'm just going to give you, this is the final example, and I promise I'll finish here in just a few minutes. I just want to give you an example of some interesting insights that we can get into groundwater hydrology by using this technique into the field. Now, this is how it's done practically in the field. Basically, we take continuous cores from core tubes, as are shown on the top left. On the bottom right, we need to trim. If drilling muds are used, we need to trim the cores to remove any drilling mud from the sample. On the bottom left, we cut it into pieces, again, depending on the type of vertical resolution that you're aiming for. And again, this whole operation, because we're dealing with core material, we don't want evaporation to happen, so this needs to happen very quickly. The core comes up, we act very quickly, hopefully within minutes, get these cores into their bags. And this is how they're stored. You can see a bunch of cores here that have been collected in the field. They're double wrapped in double Ziploc bags. The air is squeezed out of them, and they're stored in these double Ziploc bags at 100% relative humidity. And what we've done in early testing is we always took subsamples, both for squeezing and for centrifugation, because we wanted to see how well this method would produce accurate results. This shows analysis in action. On the left side, you can see a whole pile of core materials have been left equilibrated in their double Ziploc bags, and they're ready to be analyzed. And on the right, you can simply see that we've taken, in this case, it's a Picaro analyzer, and we've simply hooked up the sampling port for vapor, and using a needle on the end, simply puncture it into the bag and sample the headspace. We also prepare laboratory standards to go along with this, and they're measured frequently. The headspace sampling is between 60 and 120 mils per minute, and using this, along with standards, we can measure roughly 30 core samples per day, including standards. If any of you have history with toluene distillations or squeezing and those sorts of things, you can imagine this is a huge improvement in sample throughput. I'm just going to give you one example here. I'll need to explain this just a little bit, but bear with me. This is a site in southern Alberta where we looked at a historical site where groundwater monitoring had gone on for some time. And you can see that there's a number of boreholes installed here, and we see the geology here. There's this brown bedrock on the bottom left, and we have glacial till over top, and basically some some coarse fluvial material. And what we did is we came back to this, and the red, we're revisiting historical data. So the number 5, for example, on the left shows a number of multi-level wells that were installed years ago. And we went adjacent to many of these wells, and we took a single core going down, well, more or less next to these wells. And here's one example that I just want to show you. This is a Google Earth view of the field site where we've had pre-existing wells and where we took cores. And on these cores, we conducted both squeezing and the core equilibration, and of course we had the previous data from the wells. Now, this is the result. Now, this is fascinating. If you look, I'll just orientate you here. These are 4 of the core holes. And the yellow material is sand, and the bluish material is aquitard clay material. Now, let's start on the far figure on the right. You'll see the little triangle at the top. That's the water table. You see a green dot with an error bar on it, just slightly down from the top on the far right panel, and one near the bottom. Those are the existing wells. The blue dots are the core equilibration, and the red dots are the squeezed samples. Now, you can quickly see here that the core equilibration identically matches the water that was squeezed from these cores. But what's far more interesting is how to interpret this. The previous interpretation would have been based on monitoring wells, and all you have are 2 points, one near the top and one near the bottom. Now, if you look at the delta value down at the bottom, this is just showing deuterium, we quickly see that this is glacial water at depth. And so the interpretation based on wells would simply be, well, it looks like we have pretty close to modern water near the top, and it looks like there's glacial water at depth, and that's about all you can say. Now, what you see here is a beautiful diffusion profile. The nice thing about diffusion is the diffusion coefficients for these isotopes are well known, and so it's very easy to put a model fit, knowing the boundary conditions to this, and you can see that you can very quickly get a time series or a time determination based on the modeling of this. Now, the other really interesting one is the one that's second from the right, so this one called EMS DP1114. If you look at that, you see the monitoring wells again, top and bottom. You have modern water and so on. But look at the bottom of the second yellow aquifer. All of a sudden, you see this massive, complete break in the isotopic composition going from about -130 to -170, and there is no interface. We originally thought this was a problem, an analytical problem, and repeated it and found the exact same profile. So what we see here now is overall there's this glacial profile, but these transitions like this are something you could never have picked up with traditional methods. So here, this type of high-resolution sampling with your laser can open up new insights into your hydrogeology. Okay, just to finish up, as mentioned before, the lasers are a cost-effective solution for waters. And using great care and templates, I think you can find that your laser will perform equal to or exceed that of certainly continuous flow instruments, and we're getting there for 18. Data processing can be made more easy using LIMS for Laser software. But again, precautions should be taken that you screen your results for spectral contamination. One of the outstanding things still is areas of development are needed for front-end peripherals to make full advantage of the water vapor, for example, and those are areas that hopefully would go into the future. And that's all I have. I just want to thank a few people that contributed to the work, some of the work that I presented here. I certainly thank LGR and Picaro for encouraging our testing approaches here at the agency and in facilitating laser spectroscopy by assisting with LIMS for lasers. And then finally, I'll just leave you with a list of some selected references that may be of use to those starting for the first time. By no means complete, but somewhere that you can have a start for reading. And I believe I'm probably over time, and that's it.